Today's goal is to write the equation of a transformed exponential function. This goal is virtually the same as yesterday's, except you can tell we're dealing with exponential functions that have been further transformed. So let's start off with example 1. We can see this function is exponential based on its shape. We know the general form for an exponential function is f of x is a times b to the x, where a is the y-intercept. That's clearly at 3. B is the multiplicative growth factor. So I'm looking, okay, to get from 3 to 7, oh, this is a little weird. You would multiply by 7 over 3, so about 2 1/3, or not exactly 2 1/3. And then to get from 7 to 15, you would multiply by 15 over 7ths, which is not the same as 2 1/3. And then, already from -1, its x value is 1, to get from, its y value is 1 rather, to get from 1 to 3 you would multiply by 3. So already we're coming up with a problem because we can see that it appears as though there's an inconsistent multiplicative growth factor. So that's why we need a new strategy today. This function has been transformed from the original shape of an exponential function. How do I know that that's true? Check out its horizontal asymptote. The horizontal asymptote here is not the x-axis. The function has been shifted 1 unit down. There are 2 different ways that you can write the equation of this exponential function. Let me show you strategy 1. Strategy 1 is to say, okay, we're taking this general template, a times b to the x, we're going to move it down 1 because we can see that the function has been moved down 1. And now that we have a revised template to put our values in, let's just substitute some points. A really easy point to substitute in would be the y-intercept, because when you put 0 in, b to the 0 power is just 1, and we know that f of 0 is 3. So when I substitute this x and y value in, I get 3 equals a times 1 minus 1, so 3 is a minus 1, so a must be 4. Nice. Now I can substitute any other point I wish. I'm going to hunt for an easy point to find. It looks like 215 works nicely. I'm going to substitute 215 back into our revised form, our revised template of an exponential function. And I've figured out a, so I'm going to substitute that in. So now I've got, let's add the 1. 16 is 4 times b to the x. Divide both sides by 4. Oops. I could substitute in the x value we're dealing with. This is the x value 2. So 4 is b squared. So b must be positive or negative 2. Well, if b were negative, multiplying by a negative number would cause your y values to jump above and below the x-axis because you would get positive, negative, positive, negative. So we'll just deal with positive 2. So by substituting 2 points into my revised template, I was able to figure out the a value is actually 4. Interesting. This is no longer the y-intercept if you have transformed the function. And my multiplicative growth rate did not appear to be consistent before, but it will be consistent if I revise my template. So this is one way to do it. The other way to do it would be to take these points and shift them back up. If you move this point 0.3 back up to 0.4, I'm moving the y values up 1, since my horizontal asymptote is typically 1 unit above where it is right now. Let's take the point 1, 6, 7. So the point 1, 7 will move up to 1, 8, and we're going to move this point up to 2, 16. Now the pattern is clear. To get from the y value 4 to the y value 8, you're multiplying by 2. To get from the y value 8 to the y value 16, you're multiplying by 2 again. So we know that the function must look like a times b to the x, and then we'll have to drag it back down 1 unit. It looks like the function 4 times 2 to the x after you drag it back down 1 unit. So notice you get the same equation either way, whether you want to physically move the points back up 1 unit or you want to substitute in 2 different points. Okay, let's check out a few other examples for today. Write the equation of the function shown below. Again, there's not a consistent growth pattern here. Some number other than 6, right? right? There's not a consistent growth pattern because we can see that the function has been transformed. These y values are all approaching 3, which means we've got some shape. In fact, it looks like the y values get decreased, right? These are getting more and more and more negative. And it looks like they're getting close to 3 up top. So this is a clear transformation from my regular shape of an exponential function. And by regular shape, I mean it should increase at an increasing rate, and it should have the horizontal asymptote y equals 0. Again, there are 2 equivalent but different strategies. One strategy, which we showed first, is to revise your template. It's not going to look like a times b to the x unless we notice that we're going to have to add 3 to get these y values really, really close to 3. And we're going to have to make this a negative a to flip these y values so that they're now negative, or reflected across the x-axis. Now we can substitute in a point. I like to substitute in the y-intercept. It has the y value -2 equals negative a times b to the 0 power plus 3. And we're going to solve for a. Subtract 3 from both sides. Divide both sides by -1. We get a is 5. Nice. Now I'm going to substitute in any other point that I wish. Let's choose an easy one with small values. Again, we're going to substitute it into our revised version of the template. That means it's not just a times b to the x, it's negative a times b to the x plus 3 to reflect these 2 transformations. And we know that a is 5. So we have -12 equals -5 times b plus 3. We'll subtract 3 from both sides. Divide both sides by -5. Okay, so we figured out a is 5, b is 3. We substitute these values back into our revised template. So we have f of x equals -5 times 3 to the x plus 3. Of course, the other way to do it is to untransform the values. That means we can see that the values have been reflected. We can see that they've been dragged up 3 units. That's why we have this horizontal asymptote of 3. So actually, even if we just deal with the horizontal asymptote, let's add 3. So this would be 5.9, blah, 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 and 5.8, blah, 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 and oops, we need to subtract 3 to move it back down, right? We want to move this horizontal asymptote back onto the x-axis. So let's subtract 3. You get some sort of messy numbers here, here, and here. But if we subtract 3 here, we get -5, -15, -45, -135. Already the multiplicative pattern is much clearer. We're multiplying by 3 each time. So we have f of x is a times b to the x plus 3, so that we can drag these y values back up to their horizontal asymptote at 3. And we have f of x equals, now a will be the y-intercept after I untransformed or moved the y values back. So we're going to use -5 times the growth factor of 3 plus 3 to move the y values back up. Again, you get the same function either way. You will be allowed to choose either strategy, whichever one makes the most sense to you. One final question today. Explain how the function f of x equals 5 times 2 to the -x over 3 minus 4 differs from the related exponential f of x or y equals 5 times 2 to the x. Okay, one thing I noticed that's different is this negative sign. This negative sign is going to cause a reflection across the y-axis. So our parent function increases at an increasing rate. Now if you flip it around, it's going to decrease at a decreasing rate. Another thing I noticed is the 3. The 3 is going to cause a horizontal stretch. The function is going to look much wider now. And the final difference I notice is this -4, which will shift the function down 4 units, dragging the horizontal asymptote to y equals -4. So we've got this wide function that's been reflected across the y-axis and shifted down 4 units.